All right, guys, can you guys hear me? So give me a signal when you guys can hear me, okay? Okay, perfect. So let's give it one more minute while we're receiving more attendance. Today is a new lecture, a new session, right? So we're going to be having some new students joining us. So we might have some technical issues, so on and so forth, as a common practice. So let's give it one more minute while we're receiving more attendance. This is a new lecture for our session 6. Our AMC bootcamp is completed in the last week. So today is going to be a new lecture, a new session. Okay. In today's session, we're going to focus on the trigonometry, right? All right. So let's give it one more minute while we're receiving more attendance. So by the way, how do you guys like the AMC exam? Any updates? How do you think the exam? We just finished the AMC A, right? AMC 10A and AMC 12A. How do you like the exam? Is it fair, easy, difficult? You guys can give me some updates in the group chat, okay? Because we really like to say, how do you guys think the AMC exam? It's kind of okay, fair? Okay, that's good. Yeah, because normally we're gonna make sure we're trying after. Yeah, so normally we just want to have some feedbacks from the students, right? So our bootcamp lectures, how do you think our bootcamp lectures, all the information, all the knowledge we introduced in the bootcamp lectures, is it really helping you doing the problems, so on and so forth? Feel free to give me some feedbacks in the group chat and we'll be able to take it from there. All right, so let's get started. Okay, now we're gonna go to a brand new session. This is gonna be our knowledge-based lecture, session 6, trigonometry, complex number, and also the planar vectors. All right, so before we get started, let's spend a quick time talking about what we're gonna talk about. What are the preview of our lectures? Okay, so I'm gonna show you what we would like to cover in our session. Okay, there you go. These are the topics we're going to talk about in our 10 lectures. We're going to use 10 lectures to cover all those concepts under the big umbrella of trigonometry, complex number, and vectors. We're going to get started with some trigonometry basics, some basic introductions. I'm pretty sure you guys are already an expert, right? And then moving forward, we're going to go to the trigonometry function and problems, and also some properties of this trigonometry function. And then we're going to spend most of our time talking about the trigonometry identities, which is a very important part. Because whenever people talk about the trigonometry, there are so many formulas to remember. There's so many identities. Sometimes people get pretty drowsy. What can I do with all those weird identities? So we're going to sit down together talking about how to remember all those identities. And most importantly, how to utilize these identities in different kind of problems. You know, since we have tons of kind of like identities, formulas, sometimes you need some conditional react and some hints. So as long as you see some kind of like a signal word or kind of like signal number, you need to use a certain type of identity, which is going to help you to solve the problem. So we're going to spend the majority of our time talking about how those weird identities and how to use them. And moving forward, we're going to talk about the trigonometry and its application in 2D geometry. As we can think about it in our previous lectures, we have mentioned that for 2D geometry, you can either do the regular way, how to use all those similarity, congruency, solve the problem, or you can use the pure algebra way, aka our coordinate geometry, right? This is pretty much what we talk about in our previous lectures. And also today we're going to introduce the third way. You can actually use with the help of the trigonometry, also help you to solve some weird 2D geometry problem. So trigonometry way is something pretty much in the middle. You have the pure geometry way using all those all those kind of like a theorems, doing similarity, so on and so forth. Or you can use 100% algebra way, right? Or something in the middle, you can actually use the trigonometry way. We're going to talk about in today's lecture. Moving forward, we're going to talk about the inversed trigonometry function. This is not super important, I have to say. However, from time to time, especially from the AIME level, they like to test you a little bit for the reversed trigonometry function. And we like to sit down together, give you some ideas how to do the inversed trigonometry. And also, we're going to talk about some trigonometry equations, trigonometry inequalities. So equation and inequality, they're pretty much the same thing. You have a trigonometry expression on the left. Equation means equals to 0, and inequality means either greater 0, lesser than 0, so on and so forth. We're going to try to have a look at it, how you're going to deal with all those problems. And moving forward, we're going to come to a complex number. Complex number is kind of like a concept you guys won't be very, very familiar, right? Because from time to time, when you talk about a complex number, people more think about this is going to be, some imaginary numbers, so on and so forth. So actually, complex number is actually a very important part in the AMC 12. And it is not one of the not too many parts which makes the difference between the AMC 10 and the AMC 12, and also our Canadian exams as well. So we're going to talk about the complex number. One of the most important things to denote or to represent a complex number is using the trigonometry way. And that's the reason why we like to talk about how to basically understand the property of the trigonometries and also use them in a complex number. So applications, so on and so forth. Also the 2D and 3D vectors and their application. You know what? We're still going to talk about something about the vectors. Vectors is something which quite similar to the complex number. Of course, they have some differences for sure, but generally speaking, there are some differences and there are some similarities between the vectors and the complex number. We would like to take this opportunity to give you guys the idea how to basically leverage whatever you learn from the complex number, how to utilize them into the planar vector or even the 3D vector. Also, the vectors can also help you, try to solve a lot of weird 2D geometry problems. So at the end of the day, after our lectures, you're going to have multi ways to solve the 2D geometry. The typical way, like the real Euclidean way, or using the coordinate geometry, or using the trigonometry, or using the vectors. We're just trying to give you guys kind of a portfolio of tools. You can try to use whatever tool you think is the best and solve the problem accordingly. And also, we're going to talk something about the difference and the similarities between the complex number and vectors. So this is kind of like an overview what we're about to cover in our basically 10 lectures. So as an advanced lecture, I wish you guys have some basic ideas for the trigonometry. You don't really have to remember every single thing. That's exactly what we're going to talk about altogether. But basically, the basic definition, how this trigonometry concept is involved, so on and so forth. This is kind of like necessary for you guys to understand the entire lecture. If you have some problems or some issues, so on and so forth, let me know, and I'll be able to provide you some materials. So far, so good? Is it all good? Perfect. If all good, let's jump to our first part. Today, we're going to talk about the first part, trigonometry basics. This is going to be our lecture number 1, trigonometry basics. So no matter what, when you learn new concepts, right, you want to be asking your teacher why we have to introduce such a concepts. For instance, whenever we want to introduce something about for instance, the equation, right? Equation is kind of giving us a variable. From a variable, we want to have a relationship between several unknown things. And hopefully from this relationship, I can solve the equation or solve the relationship to get what you need. Something like that. But why we need to talk about the trigonometry? So trigonometry was actually introduced when people basically have some introduction about the 2D geometry, most likely in our right triangle. Right triangle, right? When you have a right triangle, you have maybe A, B, C, you have an angle theta. So basically, the trigonometry was kind of like an investigation that as long as I have a triangle with ABC 3 sizes, let's say I have an angle here, theta. What is the theta's relationship between A, B, and C? As long as I have ABC 3 values already given, how can I use these 3 values, try to identify what is the theta, so on and so forth. So long story short, well, the big question is we try to find out a relationship between the angle and also the side. Okay, if you can recall what we introduced in our first lecture, talking about the entire geometry. Geometry, basically, you're going to talk about 3 major things. Geometry, you want to talk about the angles, you want to talk about the size, and you want to talk about the area. Still remember, this is what we talk about in our lecture number 1. So for most of the geometry problem, they'll be asking either of the 3, right? And intuitively, why they want to ask you this? Angle, side, area. What's the relationship between these 3 things? Especially, what's the relationship between the angles and size? So this is actually a very intuitive question, right? So actually, trigonometry is a topic that we like to give you guys kind of ideas or some of the strategies how to build up the relationship between certain angles and the certain sizes. So this is basically where we come from. Okay, so let's go to our first part. We want to talk about our definition. These are something super, super basic. How trigonometry, this concept, was actually defined. So talking about the definition of the trigonometry, we actually go for 2 different steps. Step number 1, we actually understand the trigonometry from the triangles perspective. Okay, this is the most straightforward, the most easy peasy part, right? Let's say I have a triangle A, B, C. This is A, this is B, this is C. Let's say I have a theta here. So in this right triangle, I just basically defined, okay, we have the trigonometry. Let's say I use, let's say B over C, okay? B over C. We use such a ratio between B over C. We define this as a sine theta. Sine theta, this is only a definition. There's no reasoning why this is sine, why I didn't call it tangent, unfortunately. This is the people defined, right? From the definition. Sine theta is defined as what? The ratio between the opposite side and also the hypotenuse. This is quite understandable, right? Then we have the cosine theta is A over C, the adjacent side over the hypotenuse. And the tangent theta is B over A, the opposite side over the adjacent side. There's no reason. People just like to give us such a definition. That's it. So these are actually the 3 most important trigonometries. And most of the time, the AMC or Canadian exams is going to focus on these 3 major stuffs. And actually, there are also 3 not that much important, but also you're going to see that from time to time. One is the cosecant theta. One is the secant theta. One is the cotangent theta. Cosecant theta actually equals to reciprocal of sine theta, equals to C over B. Secant theta equals to the reciprocal of cosine theta, equals to C over A. Cotangent theta is the most familiar one, is the reciprocal of the tangent theta, which is A over B. This is quite understandable, right? So again, these are nothing but a definition. There's no reason why they like to use such a weird denotation, right? Why do not they change something different? There's no reasoning. So all those kind of trigonometry identities, trigonometry formulas or denotations were created a long time ago. People just by the time they're using their kind of like this, like their discrepancy to basically make the decision. So in our regular high school territory, most of the focus is going to be the 3. These are the most important. Well, you won't see that much often. Beside, I mean, not to say the cotangent, you're going to see that from time to time, but the sine theta, cosine theta, tangent theta are the most important. Talking about the cosecant theta, secant theta, this is not something that much important. Okay, just give you guys some idea, and we are good to go. Okay, this is actually step number 1, talking about the trigonometry. I think everyone knows this, totally no problem. All right. However, with our knowledge of mathematics is evolving, our understanding for angles is not only squeezed in a right triangle, right? So that being said, we have to go to our step number 2 definition. So what is the step number 2 definition? Like I said previously, in step number 1 definition, everything is actually squeezed in a right triangle. So your angle, how much you can go? Your angle is basically from 0 degree to 90 degree. That's it. If you're talking about acute angle, right? Even though you want to broaden the eye a little bit, you want to go to any kind of regular triangle, but your angle can basically go no more than 180 degrees and 0 degrees, right? Most of the discussion is pretty squeezed. However, our understanding for the angles is actually evolving. We might see an angle super big, 3065 degrees, right? We might even see a negative angle, right? We might see minus 30 degrees. We might see 3750 degrees, so on and so forth. So that being said, if we still squeeze our discussion in a right triangle, or even though in a regular triangle, they just can't offer what we need, right? So that being said, we have to, there's no way around, we have to expand our definition for the triangle, for the trigonometry into something not only just from 0 degrees to 90 degrees, from 0 degrees to 180 degrees, we want to see something bigger, something wider. And how can we do that? So we have to go to the second category of definition. We're going to go to a unit circle. So what is a unit circle? That one, everyone knows that, right? A unit circle is basically a circle, right? It has its, let me try to change it. It basically has its center in the orange, right? And you have such a circle. Okay, so now we make such a definition, or kind of like an agreement with everyone. As long as I have a side, let's say, I just want to give it this, let's say OP. Okay, so this is kind of like a ray, right? Okay, I want to define the angle from the positive direction of x-axis all the way anti-clockwise, positive direction plus anti-clockwise. Okay, we want to use such a way to define an angle. For instance, I have an angle here. I want to say this is 30 degrees. Again, this is nothing but a definition and our mutual agreement. Okay, there's no reasoning. We just like to do it. Okay. Okay, if that's the thing, people's understanding for angles can be somewhat expanded. For instance, if my angle is here, this is 30 degrees, right? If my angle is here, this can be, I don't know, maybe 120 degrees, whatever. If my angle comes to here, this can be 100, maybe 100, like 250 degrees. Or this angle goes to here, we're going to go to such a thing, maybe 330 degrees. So that being said, I can actually define a bigger angle, not only to 90 degrees, so on and so forth. And also similarly, if I do the same thing, but I want to do the same thing from a different direction, I'm just going to give you this. Let's say, still the same angle, right? Exactly the same thing. But this time, my thing goes from here. This is not anti-clockwise. This is actually clockwise, right? I can turn my ray from the clockwise direction. In that case, I'm going to be able to define a negative angle, right? Let's say this is negative 30 degrees, right? This is negative 120 degrees, so on and so forth. So that being said means what? With such a unit circle, I would be able to define positive angles and negative angles. It really depends on the direction. If you go for anti-clockwise, you're going to end up with the positive angles, which is pretty much the case we're talking about. Or if you go for the clockwise direction, you're going to be able to define negative angles, right? I think these are something quite understandable. You guys already know that. And also, if we go back to our positive thing, another example, sometimes if you do you use the color black, okay? Sometimes, or maybe color red, okay? If you do a full circle, it comes back to the orange. So that one is going to be 360 degrees. But you can continue. You can do the second turn. You can do the third turn, so on and so forth. So that being said, you would be able to define as big, like however big angle you like to define, right? You can just keep letting it turning around. You can do like 10 to the 10th power degree, so on and so forth. It's up to you. The same thing, if you do it anti-clockwise, you get the positive. If you do it clockwise, you're going to do the negative angle. Again, you will be able to define different negative angles, so on and so forth. So this is actually our understanding for the angles are actually expanding, right? Not only like tiny angles, now it's going to be huge angles, no problem. All right. With all those information in hand, it is quite possible that we like to see how you're going to expand our definition for the trigonometry. Now you're going to be looking at a huge angle or a huge negative angle. I can no longer use the opposite side or like the adjacent side because there's not such a there's not such a right triangle for you to define. So that being said, we have to find a new way to define what is the trigonometry value, how to basically facilitate or adapt our old definition into the new way. So this is how you're going to do that. Again, I'm going to use a circle here. So let's have a quick look at how we're going to expand our definition to the unit circle. So now, regardless, so let's say I have a ray here, okay? Regardless, my ray is actually turning around 300 circles, clockwise or anti-clockwise, I don't really care. At the end of the day, this is going to be your final decision, right? This is your final position. So let's say this is O, this is P. Okay, in that case, your P point is going to have an intersection with your unit circle, right? Let's say XY is the coordinate, and R is actually the radius. For our case, unit circle can be R equals to 1. Okay, in that case, let's try to, again, we're going to define. Again, there's no reasoning, we just define. This is the theta, okay? We just define such a theta. Sine theta equals to what? Y over R. The Y coordinate over the R is the radius. Again, you can turn like basically 3,000 circles, it doesn't matter, but as long as you stop, you will be able to have a coordinate, right? Sine theta is defined as Y over R. Cosine theta is defined as X over R. Tangent theta is defined as Y over X. It's pretty much the same thing as we did in our right triangle, but now bear in mind, this theta might not be only 30 degrees. It might be 3 million plus 30 degrees. It has been around a lot of circles. You can't really squeeze it in a triangle. But using our definition from the unit circle, as long as you stop, you would have a coordinate for P. As long as you have a coordinate for P, you're going to understand that this is our definition. That's it. So the same thing, the cosecant theta equals the reciprocal R over Y. Secant theta, reciprocal R over X. Cotangent theta, reciprocal X over Y. Right? I think this is kind of very understandable stuff. Again, if you talk about everything into a right triangle, into a relatively acute angles perspective, let's say my theta is only 30 degrees, it's really 30 degrees. Is it the same thing as our definition from the right triangles perspective? Of course. Given an example, let's say if your theta is just 30 degrees, I want to make a, basically you can see in this blue triangle, right? So this is going to be your Y, This is going to be our x, this is going to be r. So sine theta is exactly equals to opposite side over the hypotenuse. So that being said, there's two ways of definition. They're basically identical, right? They're talking about like the same thing. All right, I think this is like the basic definition for the trigonometry. Okay, so second part, what I want to say is that as long as you're dealing with the trigonometry, we have to deal with angles, right? You know, typical way, we would like to give like 30 degrees, 60 degrees, so on and so forth. But moving forward, we like to stop using the real angle degrees. On the contrary, we like to use kind of like the radian. There's another way to define 30 degrees, 60 degrees, so on and so forth. So what is the radian? Radian, again, is nothing but denotation. There's nothing special. So 0 is equal to 0. Let's say this is our angle. This is our radian. Okay, because these are so basic stuff. Let's say 30 degrees is actually equals to what? Pi over 6. 45 degrees, pi over 4. 60 degrees, pi over 3. 90 degrees, pi over 2, right? 180 degrees, pi. 360 degrees, 2 pi. So this is nothing but, again, it's kind of like this is like a denotation, and this is like a definition. So you see, at the very beginning of trigonometry, we actually define a lot of stuff. You just have to remember it. You just have to take it. There's no reason behind it, right? I think you guys should be 100% familiar with all those information. So that's pretty much what I want to say for the definition of a trigonometry. There's nothing really special, nothing too weird, right? I have to say, testing the trigonometry's definition used to be a hot topic. I'm talking about maybe like 10 years ago, 20 years ago. Every time you're gonna, as long as you go to AMC, you go to the American, Canadian exam, you're gonna see a lot of problems talking about the definition of the trigonometry. But these days, they're not that much popular, I have to say. As long as they like to test you the trigonometry, they're gonna directly jump to the identities. So that being said, these days, the testing for the trigonometry's basic definition is not as popular as it was. Okay, but again, try to have some basic understanding for the trigonometry's definition, introduction, still going to be very helpful for us to understand the trigonometry and where we come from. Okay, that's pretty much what I want to say for the very beginning. Let's go for some problems. We always want to use some real problems from a Canadian, American, some international math competition, put them together, help you guys understand where we come from. So let's go to some basic problems, not some crazy problems, because these are very easy concepts, I have to say, right? So the first one, we're looking at a problem that comes from 2007 AMC 12B, question number 19. Like I said, you won't see very latest problem, but back to 10 years, 20 years, there were a lot of problems. So let's have a look, quick look. So like a rhombus ABCD has a side length 6. This guy is rod to form a cylinder of a volume 6 by taping AB side to DC side. Then what is the sinusoid value of triangle ABC? Okay, like I said, from day one, as long as you're dealing with any geometry problem, the most important thing is what? You're trying to have a nice graph, right? Taking from there, from the nice graph, you will be able to help you find out what you're going to do. So this is going to be something like this, 6, 6. Okay, you have, this is going to be your A, B, C, D, right? This is 6, 6. So what you're going to do, you're going to roll this, this is diamond shape, right? Into a cylinder. So as long as you go for a cylinder, you might go for something like this. This is going to be our cylinder, right? But this is going to be AB. This is going to be what? A, B, C, D, something like this, right? Because there will be tapping all together. Okay, the question says, after you roll them, the volume goes to 6. With all the information, what's the value for sine ABC? Sine ABC is the same thing like sine ADC. Okay. So how to do such a problem? I think this is like a basic definition for a trigonometry, right? So by definition, if I like to calculate the value for sine ABC or ADC, what I have to do is I need to go for H, right? This is very intuitive. So sine ABC is equal to H over 6, right? As long as you get a value for H, then plug into this formula, you'll be able to get a value for sinusoid. Okay, who can tell me, how can I get a value for H? Let's try to have some quick ideas. How can we get a value for H? Apparently, the question just give you two things, right? The question just give you two conditions. One is the volume is 6. The other one is the side length is 6. And you're basically gonna figure out a value for H using these two things. So maybe I'll give you 30 seconds. Think about it. How can I use these two conditions to yield a value for H? Maybe we're gonna ask Alex to give us some ideas. I see Alex already have some ideas. Yeah, maybe you can talk. Yeah, I can hear you.
Circle, which is 6.
Mm-hmm.
Times radius, the area of the circle on the top, and then the volume.
Yeah, perfect. Exactly, right? This is very clear, right? This is such a simple problem, right? So what you're gonna do is you're basically gonna do the problem like this, right? You're gonna do, let's have a quick look. You're gonna do, you see, after you roll the shape, the H keeps the same, right? H doesn't change. So the volume of the cylinder is gonna be what? Equals to S times H. S is the area of the bottom times H. So what is S? Pi r squared H. Then what is R? How can we define R? R is not difficult because at the very beginning, this is going to be your one side. But now your one side has become what? A circle, right? So this one side actually becomes the perimeter, right? The circum of this entire circle. So that being said means what? 2 pi r equals to 6. So you will get a value for r 6 over 2 pi, right? Easy peasy. Plug in the value. This is 6. This is everything 6 pi. You will be able to get a value for h. H is what? 6 pi over 9, right? So easy, right? As long as you get a value for this, you plug in this value to here, you'll be able to determine the sinusoidal value of such an angle, which is what? Pi over 9. That's it. Easy peasy, right? So this is actually nothing but a basic definition. All right, if all good, let's go to our second problem because these are so easy, right? We don't have to explain too much. Let's go to our second problem. Our second problem is a problem that from Canada. It's a Euclid problem. Just drag it from here. This is a problem from 2002, Euclid. Question number 9, A part. Okay, like I said, the Euclid, the first 7 problem are always easy. It's only 8, 9, 10. They're relatively difficult, right? And there might be some discussion, some thinking you need to do in order to make it work. So let's have a quick look. So the question says, in a triangle ABC, the ABC is equal to 90 degrees. So this is 90 degrees. Rectangle DEFG is actually inscribed in triangle ABC. Okay, so let me try to highlight it. So this, like the blue one, is a rectangle. Okay, no problem. as shown. And you have two squares, JKGH. Okay, this one is a square, like the little red one is a square. And also MLFN, this one is also a square. Okay, you have two squares and one rectangle inscribed, right, into this right triangle, blah, blah, blah. If the side length of JHGV is actually V, okay, this one is V, this one is V. And also the side length of MLKF is W. This is W, this is W, okay? And DG equals to U. DG, let me change a different color. DG is here, equals to U. With all those information, the question asks you to determine U is equal to V plus W. U is equal to V plus W. Okay, U equals to V plus W. From our trigonometry's perspective, we don't want to say too much at the very beginning, but from pure geometry's problem, if you want to make sure, okay, one side have a relationship between another side, so on and so forth, most likely you want to put them into a triangle, right? Or at least put it into a quadrilateral. Hopefully you can do some magic and taking from there, solve the thing. However, check it out, UVW, there are basically three side lenses, right? There's kind of no way for you to put them into the same triangle, right? So they're totally impossible to be fit into the one triangle. So that being said, if you want to for the direct 2D geometry, it might not be that much easy. So this is the thinking process. Let's try to talk about the thinking process. Number one, let's try to do the pure 2D way. Hopefully, we're going to put them together into a triangle and hopefully doing some congruency, so on and so forth to make it work. But these three sizes, I don't think you can put them into a triangle. At least there's not such a triangle for you to deal with. Second way is, can we do the coordinate geometry? Well, trying to do the coordinate geometry is kind of okay, but because first of all, before you do the coordinate geometry, you want to have some perpendicular lines, right? And you will be able to construct all your, all your coordinates and taking from there, do the work. But even though you have a bunch of right triangles, you have the x-axis, y-axis, you are dealing with three sizes. If you want to do the coordinate geometry in three sizes, you're probably going to do what? X1 minus y1, y1 minus y2, right? Something like that. You're going to deal with that 3 times, which is kind of a nightmare, right? You need to get, let's say you need to get the coordinate of G, D, right? Try to present the U. You want to get a coordinate to G and J and K to present V. And you want to get a coordinate to about these two things to present W, which is okay, but still you're going to take a lot of efforts to find all those kind of angles and figure out all those coordinates doing the huge calculation, which is not our best practice neither. Then what about our number 3, the third approach? As long as we have no way to do the 2D way, we have not so easy to do the coordinate geometry. Like I said, sometimes trigonometry can help you do some work. Okay, if we want to talk about the trigonometry, normally speaking, I still want to put them into a right triangle using the definition, so on and so forth. So who can tell me what kind of 2 or 3 or more triangles it can accidentally, if I use the word, right, or happily to basically retain all those segments, the V, the U, the W, so on and so forth, right? You need to have as much information as possible into the same triangle and hopefully doing some trigonometry and make it work. Who can tell me from such a graph, reach maybe 2 or maybe 1 or maybe 3, I don't know, triangles has the most touch with most of the UVW segments? Who can tell me? You need to understand the thinking process, right? If I randomly give you a triangle, I just want to give an example. Let's say if I choose a random triangle here, and let me change the color maybe to black. Okay, I choose a random triangle here, but this triangle is touching nothing. It only touches like W, right? This is W. Oops, let's try to say this is W, right? This one is touching a W, which is good. However, besides W, it has nothing to do with all the other segments. Of course, you can't choose it because you won't be able to elaborate your calculation. You must have to find a triangle which get touched with all those segments, and then taking from there, you get what you need. So maybe we can ask a Clement to give us some ideas. Which one do you think? Or which ones do you think is the best?
Triangle DJH and triangle ENM.
Why?
Because for DJH it touched V and a part of U, and for E and M it touched W and a part of U.
Exactly, right? So this is the thinking process, which is very important. So I'm gonna use maybe the color yellow. Okay, the reason why I choose these two triangles because they're touching the most segments possible. I'll give you some ideas why. Let's say this is going to be your V, right? I'm going to change the color maybe to black. This is V, right? And this is U minus V. Okay, this is W. And this is U minus W. Is that right? So you're touching all the segments and you're the most valuable triangle, I will be able to start my work. This is a very important process because I'm not reading the solution for you, right? I'm showing you actually the thinking process. All right, now I'm going to be able to play my work with this two triangle. Okay, very important notice. Note in bold. When you're dealing with the 2D geometry solution, you're pretty much looking for what? Similarity or congruency, something like that, right? Quite understandable. Try to find a side, an angle, blah, 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 figure them out. However, when you want to deal with the trigonometry solution, similarity, congruency is not the most important thing. The most important thing is you want to present how this trigonometry expression looks like, how the sine, cosine, or tangent looks like. You want to do the same thing for different triangles. And as long as these two triangles, they have the same angle, these two trigonometry presentations should be the same. This is a very important approach. Okay, in the trigonometry solution, you're no longer dealing with the similarity, congruency, which is not important. On the contrary, you want to present trigonometry and taking from there, solve the problem. Let's check it out. In these two triangles, I think intuitively, these two triangles are similar to each other, right? If you don't agree with me, let me try to see. If this guy is theta, this guy is also theta, right? If this guy is theta, this guy will be theta. If this guy is theta, this guy will be theta, right? This is quite understandable. There's not a rocket science. Theta, theta. You see, you already see two triangles there. You already have all the sizes, and you see the two angles are the same using our approach. Try to represent the trigonometry value on two different triangles, and then let them equal to the same, right? Because they're supposed to be the same. In this triangle, let's say tangent theta will be equals to what? Will be equals to U minus V over V. Is that right? Tangent theta, opposite over your adjacent. Here, exactly the same thing. Your tangent theta will be equals to omega over U minus, W over U minus W. Is that right? You just have to make sure these two guys are equal to each other. Is that right? So let me put here one more time. U minus V over V omega, or like W, U minus W. Is that right? You know what? Try to do some quick simplification. This guy is going to give you U square minus UV, UW, VW equals to VW. U minus V minus W equals to 0. Either U equals to 0 or this guy equals to 0. Of course, U cannot be 0. U is what? U is actually the entire length of this rectangle. So for sure, must be this guy equals to 0, aka U equals to V plus W. That's it. QE. So easy, right? If you check the Euclid official solution, there's a long solution. I don't even know what they're talking about. However, using the trigonometry solution, it's going to be so easy for you to solve the problem. See? Trigonometry, you just have to do what? Let's do a quick recap. You have to find out some triangles, present the trigonometry value, and then try to make either they're the same or they're complementary to each other, so on and so forth. It really depends on different situations. But generally speaking, present all those trigonometry and taking from there, solve the solution. That's exactly where we come from. So far, so good? If all good, let's go to another problem. Let's go to another American problem as well. So this problem, I'll give it to you guys. Okay, I'll leave it to you guys. Who can tell me how can I do this? We need to have more interactions for our lecture. 2000, this is a problem for 2004, AMC 12A, question number 21. We jump from the American to Canadian back and forth. Later, we're going to show you some other problems from other countries. So this guy, let's have a look. If sigma from n equals to 0 to infinity, cosine 2n theta, right? Cosine maybe 2 theta, 4 cosine theta a square, cosine theta to the power 4 to the power of 6, you know, so on and so forth. Sigma, everything together equals to 5. Then what's the value for cosine 2 theta? You know what? I'll give it to you guys. So try to post your answers into the group chat. And then later, I'm going to ask somebody to give us some ideas. Okay? In our bootcamp lectures, we're really squeezed. I have to talk all the time. But as long as we go to our regular lectures, I want you guys to get involved more and more in the process. Yeah, think about it and try to post your answers into the group chat. The group chat. So you don't know where's the group chat? Just basically using like the Zoom chat. So if you have no idea how to find out the chat, in your control console, you're gonna see a bunch of buttons, maybe mute, something like the video security participants, so on and so forth. And there's a one button named chat. If you click that button, it's gonna guide you to a kind of like a group chat for the meeting, right? You can choose either talk to me individually, or you can talk to everyone broadly. So if you are not so sure, you're a little bit shy, you can put your answers to me individually, so no one would be able to see your answer. But I don't think it doesn't really have to, right? You can basically let everyone to see it. This is a learning process. Okay, this problem. Okay, I'll give you guys maybe, like I said, 30 seconds, 1 minute. Think about it, what you're gonna do, and post your answers into the group chat. We already have some students. They're moving halfway through. Okay. The other students, same thing for you guys. Yeah. We already have Rina has the correct answer. The other students, yeah, try to post your answers into the group chat. We can have a quick look at it all together. All right. So you know what? Let's ask Rina to give us some ideas how to do such a problem. Let's invite Rina to give us some ideas how to solve such a problem. Hey, Rina, I can't hear you. Maybe something wrong with your microphone. Yeah, so next time try to make sure your microphone, your headset, everything is ready, because we're gonna have a lot of interactions in our lecture, and try to make sure you can participate as if you're in the real class. So can you guys hear Rina? I can't hear her. No? Yeah, I think there's something wrong with your gear. Yeah, maybe next time try to see how to make sure your microphone is working. Yeah, no problem. So let's do this next time. So for such a problem, I think at the very beginning, what you're going to do is you just basically, write, right? You only have one condition, right? This is going to be what? It's going to be cosine 0 theta, cosine 2 theta, 4 theta, all the way to whatever, right? Adding them together equals to 5. So that one means what? So that one means what? Check it out. This is exactly a infinite geometric sequence. You want to basically calculate a sum. So that was as what? It's going to be your cosine 0 theta 1 minus q, right? That one equals to 5. So easy, huh? So cosine theta equals what? This is 1. So that being said, cosine square theta equals to 5 over 4, 4 over 5, right? As long as you know the value for cosine square theta, you want to determine what's the value for cosine 2 theta, you're going to use the double angle formula. Is that right? Yeah, maybe you're not so familiar. Yeah, double angle formula is kind of in the identity, but this is not a super complicated identity. Cosine 2 theta can be written as either cosine square theta minus sine square theta, or 2 cosine theta square minus 1, or 1 minus 2 sine square theta. Is it right? This is the double angle formula for cosine 2 theta. Notice, if you're not so familiar, no problem. We're going to talk about it in our identity lecture. Okay? Today, I just want to give you something fairly easy, fairly quick, right? There are actually 3 different ways to represent cosine 2 theta. And today, because you have already know the value for cosine square theta, you're probably going to choose the one in the middle. is equals to 2 cosine square theta minus 1. So that one is going to give you what? Actually, the D option. 3/5. You see, easy peasy, right? You're not using some very complicated flowery things to do the calculation, and you will be able to do it fairly quick. Since we're talking about here, I just want to give you guys a quick note, because learning the identities takes some time. We'd better, every time we see it, I'm going to write it for you. So after 10 lectures, for sure, you will be able to remember it. So that's the value for cosine 2 theta. Then what about sine 2 theta? Sine 2 theta equals to 2 sine theta cosine theta. What about tangent 2 theta? Tangent 2 theta equals to 2 tangent theta, 1 minus tangent square theta. So like I said, in the AIME exam, sine, cosine, tangent, they are considered to be the most important trigonometry expressions, rather than secant, cosecant, so on and so forth. So as long as you remember this, the other three, you just take a reciprocal, you're good to go, right? So as long as I see them, I like to write it for you. I ask you guys, please also copy it for yourself. Then gradually, you will have more chance to remember them. Okay, this is the famous tangent or sine or cosine double angle formula. Given name, double angle formula. So far, so good? All good? I think this is very understandable, right? Perfect. If all good, let's go to one relatively difficult problem, but not super difficult. Let's go for an AIME problem. Again, we're not using very flowery, very complicated identity. We just use something very basic, very foundational. So a problem we're looking at is going to be a problem that comes from, okay, this is a problem that comes, it's a relatively old problem, 1998. AIME, question number 5. By the time then there wasn't AIME 1 or 2, there was only one AIME. Okay. Also, like I said, these kind of basic trigonometry problems, they're no longer very popular these days. So I can only pick up some old problems. These days, they want to test you, they directly jump to identity. Okay. And also you can figure out that, the complexity is actually going up. Previously, they're still testing some foundation thing, but these days they have no patient testing foundation things. As long as they want to test the trigonometry, let's jump to the identity, the most complicated identity. So let's have a look. The problem says, given that AK have such a weird expression. AK equals to K times K minus 1 divided by 2 is the coefficient times cosine K times K minus 1 pi divided by 2. Oh my God, this is a crazy one, right? It's a kind of a weird two things together. With all those information, the question asks you, what's the value, the absolute value of A19, A20, all the way to A98? Okay. So this problem, how we can deal with that? We always want to teach you the thinking process, right? The strategy rather than the solution. First thing first, a quick observation says AK this is kind of like a general formula, right? Okay, you want to use this AK to put K equals 19, 20, all the way to 98 to figure out all the sum. First thing first, as long as you see a weird, this is a weird thing, right? Still remember, right? As long as you see a weird expression, A19 all the way to A98, there's no way for you to calculate one by one and put them together, right? As long as you see a weird thing, still remember what we keep talking about for all our lectures. There are only two ways to solve it. Either this will be a pattern, right? There will be some easy peasy pattern. You can easily get them. Or this is kind of periodic function. Still remember? There are only two ways. As long as you see something, you put like so many terms together, there are only two ways. Either there's a pattern or this is going to be a periodic function. Trust me, no way around. There must be exactly what you're going to do from here. Okay, so let's have some quick observation to see how we're going to do that. If we want to go for the pattern way, do you still remember what you're going to do? You have to write out A19, A20, A21, A22, so on and so forth, right? You try to figure out what is the value, and then hopefully you find out a pattern. Trust me, if you do this, you can very easily find out a pattern. I think within 30 seconds, you write out 1, 2, 3, 4 terms, you get a pattern right away. Okay, so I'll leave it here. I will park it here. Okay, let's go to a more rigorous solution, because a rigorous solution will be exactly the same thing as a pattern. No problem. Let's do this more rigorous solution. Okay, so let's have a quick look at it about AK. K minus 1, 2, cosine K minus 1, 2 pi. Okay, this AK is actually created by two parts. One is the coefficient, and the same coefficient you times a pi, you insert it into cosine. A quick observation next tells you that K times K minus 1, these are two adjacent numbers. Two adjacent numbers, always one is odd, one is even. Is that right? So that being said, this guy is always going to generate an integer. Is that right? This is always going to generate an integer. Okay, let's continue. If this guy always generates an integer, you basically is going to talking about what? Cosine integer k times pi, right? Cosine integer times pi. Cosine integer times pi gonna be something like this: cosine pi, cosine 2 pi, 3 pi, 4 pi, so on and so forth, right? Let's have a quick look. As long as pi, cosine pi is what? -1, right? Cosine 2 pi, cosine to a +1, right? Cosine 3 pi, -1. 4 pi, +1. Oh, so that being said, as long as you're doing this positive, you're 1, 2, 3, 4, 5, 6, 7, 8, 9, 2, your cosine n pi will basically either equals to 1 or -1. As long as n is even, you go for positive. As long as n is odd, you go for negative. Is that right? Okay. So that being said, I think you will understand what you're going to do. So for the first part, you don't have very too much. This is always an integer. That's it. While for the cosine pi part, it really depends on your k times k minus 1 divided by 2. If this is even, you're going to always have the cosine value equals to 1. If this is odd, you always come to have cosine value equals to -1. So that being said, I might be able to see something like this. Check it out. If k minus 1 divided by 2, if this is even, okay, I'm going to have one result. Or this is odd, I'm also going to have another result. Is it right? Very understandable. So how to make sure this one is even? I don't think that's a rocket science. As long as k is congruent to 4, congruent to 0 modulo 4, or congruent to 1 modulo 4, you will make sure this is going to be even. This is not the rocket science, right? It's just very easy for you to figure it out. Or as long as k is congruent to 2 modulo 4, or is congruent to 3 modulo 4, I would be able to have this expression equals to odd. Very understandable, right? This is not a rocket science. So that being said, if I consolidate my writing this, my AK is going to be, as long as this is even, the cosine value will be 1. As long as this is odd, the cosine value will be -1. So therefore, my AK is going to be 1, 0 mod 4, or 1 mod 4, right? As long as k is congruent to 0 modulo 4 or 1 modulo 4, AK is going to be your positive integer, because by the time then your cosine theta is going to be equal to 1, or negative this guy when k is congruent to 2 modulo 4 or 3 modulo 4. Is it right? This is something quite understandable, right? This is not a rocket science. You will be able to understand it. Basically, based on the different value of k, you will be able to find out what is the value for AK. So far, so good? Okay, if that's the case, I think you will be able to just try to write out all the values for AK. You're talking about the AK 19, AK equals to 19, K equals to 20, 21, so on and so forth, right? You know what? Just write them out. This won't be something too complicated. You're going to find out 19 plus 20. If I put a bracket here, okay? 21 plus 22. I put a bracket, 23 plus 24. You just have to plug in the value. There's nothing really tricky. This is going to be your 19. This is going to be minus 21. This is going to be positive 23. The next one is going to be negative 25. It's always going to be what? The odd numbers, but you're going to have a positive, negative, alternatively. So if the question asks you, what is the absolute value of about everything? It's going to be what? 19 minus 21, 23 minus 25, 27 minus 29, all the way 95 minus 97. What are you going to do? Again, you're going to do it the second time. This together, minus 2. This together, minus 2. This together, minus 2. All the way, the last one is also minus 2. There are 20 pairs. So the solution will be 2 times 20. You put an absolute value, whatever, equals to positive 40. That's it. You see, this is not something super complicated, right? So let's have a quick recap what we have learned so far. So the first part is, like I said, as long as you see something weird, what are you gonna do? Either you have a pattern or you have a periodic, but you have no idea what it is, right? So what you're gonna do is, why don't you write out a couple of terms, right? So your solution number one is, I close my eyes, I just write out them one by one. I don't really have to do all my analysis. Write out number one, you might get an idea. Or doing some quick analysis, your analysis is not a rocket science. You will be able to find out, okay, the coefficient, even though it looks scary, is always an integer. The things within cosine is always going to generate positive, negative one, alternatively, based on even number, odd number. When you consolidate all the knowledge together, you will be able to find out, okay, at the end of the day, your cosine value, your AK, is nothing but such an alternative thing. And then you just have to do some quick calculation and you get what you need. This is the entire thinking process, right? You don't have to jump too much and you will be able to get what you need. So far, so good. Can I have the feedbacks? Are you guys following me? Are you guys with me? All good? Okay, perfect. I think 4 examples is good enough, right? Like I said, this part is no longer super concentrated stuff. So we have some ideas how to use the basic definition, and we will be able to solve the problem. If all good, let's go to our second topic, because all those topics are pretty much connected. So our second topic, we're going to talk about trigonometry functions. How does trigonometry function looks like? Are there any special properties or something you need to know for trigonometry functions? Again, we just focus on the most important thing, most important 3: sine, cosine, tangent, because they are the 3 musketeers, right? The most important 3 musketeers. Number 1, sine x. I think you guys already know this. I'm just going to take this opportunity to help you guys consolidate everything. We do a quick review, right? We put all the pieces together. So how sine x looks like? Sine x goes like this. This is pi. This is 2 pi. And you can keep writing this, right? Minus pi, so on and so forth. We always just want to cut for 1 cycle. Okay, this is how sine x looks like. So sine x, whenever you want to determine some properties of a function, you want to go for certain categories. Number 1, what is the domain? The domain is R, right? You can take whatever value you want to take. Second one, what about the range? Right? In our last session, advanced functions and advanced functions, we have given you guys different ways, different tools how to evaluate a function. Right? We just basically follow exactly what we introduced in our previous lecture. We want to use the same way, the same tool to evaluate such a new function. The range is from -1 to +1, right? This one, everyone knows that. Number 3, let's talk about increasing or decreasing. Sine x sometimes is increasing, sometimes is decreasing. Is it right? So for instance, we want to cut this part. In this part, sine x is actually an increasing function. So increasing is from minus pi over 2 to pi over 2. Is it right? So far, so good. And also decreasing function. Decreasing is this part. From pi over 2 to 3 pi over 2. This is a decreasing function. Is that right? Let's focus on one domain, one period. Okay. However, sine x is what? It's a periodic function, right? We all know that. Sine x is a periodic function. So that is only good for one period. That is only good for one period. You need to expand it to all those domains. This domain is entire R, right? It's not only from minus pi to pi or something. So how to make it generically to one domain? So you just have to add the period. Is it right? Plus 2k pi plus 2k pi plus 2k pi plus 2k pi. Is it right? As long as sine x is from minus pi over 2 to positive pi over 2 plus 2k pi, this is going to be increasing. Also, as long as from here, pi over 2 all the way to here, 3 pi over 2 plus 2k pi, this is going to be decreasing. So far, so good? Yeah, just want to have a quick idea. Are you guys familiar with this? Increasing, decreasing is not only for one domain, it's actually valid for the entire period. Can I have some feedback? Yes or no? If you don't understand, I'm gonna re-explain this to you. Is it all good? Can I have some feedbacks? Don't be shy. If you don't understand, let me know. I'll be able to give you some explanations. But if you don't speak, I really can't read your mind, right? So there are many students already replied me. I'm gonna base on those students. Okay, perfect. So these are, I think, the very basic definition for trigonometry, right? So number 3, we're going to talk about the periodicity, right? Sin x is a periodic function. And what is the period? Or say, what is the minimum period, right? Because we have already discussed it's a function. If a function is not a constant function, if it is a periodic function, it must have a minimum period. So the minimum period of pi of this is actually 2 pi. So far, so good? So this is how a sin x looks like, okay? And the last thing is that sin x, you can see here, we talk about the domain, the range, increasing, decreasing, periodicity. And the last one is actually the parity. Sin x is what? It's a odd function, right? Because you see here, we have already talked about if you take this, if you want to take a circle, if you want to take this, if you want to take a rotation, this is central symmetric. So therefore, it's a central symmetric. So therefore, sin x is an odd function. We have already talked about the entire thing in our previous lectures. So we just want to use whatever we talk about to discuss all the functionalities, all those properties of a sin function. All good? If all good, let's go to our second function, cosine function. Number 2, cosine x. Cosine x goes like this. All right, this is your cosine x. This is pi over 2 minus pi, right? So what is the basic properties for cosine x? Domain belongs to R. Range, -1, +1. The third one is increasing, decreasing. Increasing. Whenever x is from -pi plus 2k pi to 0 plus 2k pi, cosine x is what? Increasing function. This is this part. Whenever x is in this part, this is going to be a decreasing function, right? It's from 2k pi to pi plus 2k pi, right? Cosine x will be a decreasing function. Again, because cosine x is a periodic function, you can't only give one period. You need to give multiple period, right? Because the entire domain is ring is actually all the real numbers. So this increasing, decreasing is periodically, basically from here all the way to here, right? This is another increasing, and then another increasing, and then another increasing, so on and so forth. Number 4, what is the periodicity? This is also 2 pi, right? Cosine x is also a function with the 2 pi as the periodicity. And the last one is even odd. Cosine x is actually an even function, right? Because this is a symmetric, right? You'll be able to see y is actually the symmetric axis. So cosine x is equal to cosine minus x. This is an even function. Okay, so far so good. I think this basic definition, right? You should already learn that in your whatever schools, but these are kind of very understandable. So let's go to third one, tangent x. Tangent x goes like this. This is pi over 2 minus pi over 2. Number one, domain. Tangent x is not actually touching everything, right? Tangent x, you can't touch anything like pi over 2 minus pi over 2, so on and so forth. So tangent x is not a domain which covers everything. Is that right? This is very understandable. So tangent is x belongs to R. However, x does not equal to 2 pi plus k pi. 2 pi plus k pi, right? As long as you have like any kind of 2 pi plus k pi, k is the multiple integer of k. This k is the multiple integer, right? And then you won't be able to make this part of the domain of the tangent x, which is quite understandable. Number two, range. Tangent x, what is the range? Because tangent x is from the here all the way to here, so its range is actually R, right? Tangent x can cover from negative infinity to positive infinity. You basically cover every single value from this range. Okay. Number three, increasing, decreasing. Tangent x is always increasing, right? Tangent x, there's no decreasing part. So it's always from minus pi over 2 to pi over 2 for one period. And the period of tangent x is actually k pi, so therefore it's actually plus k pi, right? These are the basic stuff. Minus pi plus k pi to positive pi plus k pi, tangent x is always increasing because you can actually write another tangent here, right? You can write another tangent here. Tangent x is also periodic. And the number 4 is, what is the period? Tangent x, the period is pi. Is that right? These are very, I think, basic stuff. So tangent x, actually, the period of tangent x is pi. If you do a quick comparison, cosine and sine, they're basically the same thing, right? Why? Later you will understand. Sine x and cosine x, they're basically the same thing. Sine x and cosine x, the only difference, let me try to two things here, is basically you shift pi over 2, right? Tangent cosine x and sine x, the only difference is you shift pi over 2, and you will get exactly sine x to cosine x. Well, so that's the reason why most of the properties for sine x and cosine x, they're pretty much identical. However, if you go to tangent x is a little bit different. Tangent x has its period is actually pi. So this is actually one period of your tangent x. And also these lines here, I write out here, right? These are what? Asymptote, right? Asymptote of your tangent x means this is a line. Tangent x can be very close to, but it will never touch it. Very close, but never touch it. So this is the asymptote. So far, so good. Any questions? Can I have some feedbacks? Are we all good? All those concepts. Yes, no? Okay, perfect. So let's continue. So actually, think about it, in our high school territory, trigonometry function is the only function that we see the periodicity. right? Periodic function is quite understandable, right? However, we don't see a lot of like visualized periodic function from time to time. And the trigonometry function is one of the most powerful, one of the most tangible periodic function we see so far. So that being said, let's try to take this opportunity. Let's try to talk about the periodic function, because you won't be able to see another periodic function besides our trigonometry in high school territory. So let's try to take this opportunity to give some quick talk about this periodic function. Most of the discussion, I'm going to say, would be very understandable, but let's try to summarize everything all together, right? Do some summary. First one, let's talk something about the definition. What is a periodic function? So so everyone knows what a periodic function is, but let's try to use our mathematical language, try to basically do a definition. It means for any given x belongs to D. This just means for any given. It's only a mathematical denotation, just math. Like the mathematicians, they're lazy. They just want to minimize all the words. For any given x belongs to D, D is the domain. There exists a T belongs to R. There exists. Again, it's only denotation. Such that fx belongs to equals to fx plus t. For any given x belongs to D, means this property is not only for one x, every single x must follow. There must exist a T belongs to a real number. You can't give me like a complex number or something, right? A real number, such that fx equals to fx plus t. Then you can say T is a period of fx. T is a period of fx. Okay, people will say, why you say a period of f? Because if T is period, 2T is also period, 3T is also period, 3 million T is also a period, right? So we just want to minimize our discussion. T is a period. Okay, if that's the thing, that's the basic definition. Based on the definition, let's try to talk about some basic properties regarding the periodic function. Properties of periodic function. Let's try to mark it. Period property number 1. Generally speaking, periodic function fx is always defined on real numbers or all the integers. Generally speaking, periodic function, the domain of your periodic function should be wide enough, because you're always going to put T, 2T, 3T, 4T, right? So you either belongs to all the real numbers, or you can poke out several points. Let's say for our tangent x, right? There are some points not available, but generally speaking, the big range should be there. Or you can define on all the integers, let's say periodic sequence, right? Periodic sequence, you only take the integers, but still you want to take everything. Generally speaking, you cover everything. Second, if T is a period, then NT is also a period. Of course, n belongs to an integer, right? This is understandable, nothing to say. Number 3, if fx is periodic, fx is not a constant. Sometimes we say constant function is also a periodic function, which that's not really, I mean, like the constant function, there's nothing to say, right? Always fx equals to 1. Yeah, you can also take it as a periodic function. It's okay. If fx is periodic, but fx is not a constant function, so therefore, fx must have a minimum positive period on D. This is actually a very important thing. If a function is periodic and it's not a constant function, then you must be able to find a minimum positive period, which makes sense, right? So all the period we say 2 pi is for cosine, 2 pi is for sine, pi is for tangent. We're basically talking about the minimum positive period. Minimum positive period, which makes sense. Number 4. If fx has a minimum positive period t0, then besides n times to 0, there is no other positive periods. Does it make sense? If fx has a minimum positive period t0, then besides n times this t0, like I said, the periods is always the multiple, right? Multiple of their minimum period. But besides that, there's no other positive period. So this is kind of like has and only has, right? So as long as t is the minimum, nt is a period, and nt is the only period. You won't be able to see any other periods. Okay? Number 5. If fx is periodic function, then all the following functions are also periodic. Any kind of linear combination of fx. Fx take absolute value. Fx take reciprocal. Fax plus b. All those functions, they're all periodic functions. They're all periodic functions. Okay, so far so good. This is also understandable, right? If fx is periodic, then you want to take some reciprocal linear combination or even do some composed function. You don't really change the periodicity. So periodicity is a relatively very stable property for a function. Number 6. We let y equals to fx. A is not equal to 0. If for any given x, you have fa plus x equals to fa minus x, fb plus x equals to fb minus x. A and b are not the same, okay? For a function, you have two values, a and b. If you have fa plus x equals to fa minus x, also fb plus x equals to fb minus x, then fx must be periodic, and the function is 2b minus a. I want to take an absolute value. 2b minus a. I want to take an absolute value. What does it mean? Before we jump to like the proving process, so on and so forth, I really want to show you what is because learning math is the same as learning physics. You need to understand that the nature, how this one is talking about, right? In physics, right? If you only remember those kind of formulas, that's going to drive you nowhere. You're going to understand what is the physical nature for it. The same thing for mathematics. I give you these two weird things, but what does it mean? This is a mathematical language. Of course, you can, okay, I have to formula. But how can I understand in the human way? Who can tell me? From a human's language, What does this guy mean? What does this function looks like if you have fa plus x equals to fa minus x? Who can tell me? What does it mean from a human language, or from the function's perspective? What does fa plus x equals fa minus x mean? Who can tell me? Somebody says 2a is a period. No, I don't think so. A plus x equals to a minus x does not necessarily mean 2a is a period. A plus x equals to, I mean, fx equals to f2, x plus 2a. That means a is a period, 2a is a period, right? But you won't be able to say that 2a is a period. What else? But nice try though, right? What else? What does it mean? From graphs perspective, we like to make an analogy from the physics, right? From physics perspective, somebody says A is a period and B is a period. No, I don't think A plus x equals to A minus x means A is a period. No. What else? 2x is a period. X is not, x is a what? X is a variable, right? X is not. So let's ask Wayne to give us some ideas. I think Wayne has the correct answer.
Because for any given x, f a plus x is equal to f a minus x. So that means it is symmetrical against x equals to a, because the y value of a plus x and a minus x has the same value. And then that's how it works.
Is that right? You guys agree with Wayne? This guy just means what? Let me try to give it here from a graph's perspective. Let's say I have a x equals to a, right? Means any numbers on the left, on the right, the two sides of x equals to a, as long as they have the same distance to x equals to a. One is plus x, one is minus x, right? Something like this, or something like this, or something like this. They're always kind of symmetric, right? So that means that x equals to a is actually a symmetric axis. Is it right? X equals to a is a symmetric axis. This is understandable, right? What about the second part? Exactly the thing. Exactly the same thing. X equals to b is a symmetric axis, right? Oh, so that means that if a function has two symmetric axes, and they're not the same because a is not equal to b, right? As long as a function has two different symmetric axes, then automatically this function will be a periodic function. Again, how can I imagine that? Let's try to use our sine x or cosine x. Cosine x not has two, it has multiple symmetric axes, right? So that means that such a function must be a periodic function. So this is the way how you get connected from the kind of like the mathematical word all the way to the physical essence of the problem. Is that right? As long as a function has two symmetric axes, it must be a periodic function. How can I prove this? Let's try to do a quick proof. This proof is very easy. Proof. Okay. A plus x equals to f a minus x. So that means what? F 2a minus x equals to fx, right? Is it understandable? I basically let x equals to x minus a. I plug in x equals to x minus a, then automatically you have f2a minus x equals to fx. Is that right? Same thing. fb plus x equals to fb minus x. I can do exactly the same thing, right? f2b minus x equals to fx. Okay, if that's the case, I'm going to do a magic. Check it out. f2b minus, I'm going to let this x equals to 2a minus x. According to our definition, will equals to fx. Is it right? Because this is going to be your x. This is going to be your x. f2b minus x equals to fx. However, your f2a minus x just equals to x. Your f2a minus x just equals to fx. So therefore, check it out. Here equals to here. f2b minus a minus x plus x, because minus minus plus, right? Equals to fx. So therefore, the period will be 2b minus a. Let's say b is greater than a, right? Otherwise, you want to take an absolute value. So far, so good? So this is the way how you want to determine a periodic, like the period of a given periodicity. Of a given periodicity. So far, so good? Okay, this is understandable, right? Number 6. Number 6 means what? If a function has two symmetric axes, then automatically this is going to be what? A periodic function. Number 7 is pretty much the same thing. If fx is symmetric versus 2 points. Still remember, a function is either central symmetric or axis symmetric. We have already talked about if a function has two symmetric axes. Now let's talk about what if a function has two central symmetric points. A1b, A2b. They must have the same b, right? It's like the same, it's kind of like the same x. It's the same y, but only different x. A function, if a function has two central symmetric points, this function must also be a periodic function. And the t will be 2a2 minus a1. Same thing. I want to take an absolute value. Okay? If you can't really buy it, can you use the same thing, sine x? Sine x also has multiple central symmetric points, right? As long as you go to x equals to 0, this is going to be central symmetric points, right? So that being said, if you have two, you have multiple, whatever, then you will be able to determine what is the period of your function. So what is the periodicity? Twice of the difference between two adjacent periodic points. So far, so good? Feel good? Let's go to number 8. Number 8 is also let fx, if you have fa plus x equals to fa minus x, this is the same thing, right? Fx using x equals to a as the central, as the axis, like the symmetric axis, and this time it's going to equals to minus fb minus x. Okay, if this is positive, this is exactly the same thing as our previous property, right? You see, the only difference is previously this is positive. Now, this is no longer positive, this has become negative. Okay, this is the only difference. One is a symmetric axis, no problem. The second one is not symmetric because it changed the sign, right? But generally speaking, it's quite similar. If that's the same, fx must be periodic. And the minimum positive period will be 4 times b minus a. Take an absolute value. Okay, check the difference. Previously, this is what? This is 2 b minus a. If you have two symmetric axes, aka the second one is positive. However, if you switch the second one into negative, this is going to be exactly the same thing, but it goes to 4 times b minus a. This part, I'll leave it as a homework. Think about it, how to do a proof for such a thing. Yeah, we already give the proof for the previous one, right? Very easy proof. Try to use something similar, just a very, very tiny difference. And you will be able to find this one is pretty much the same proof. So far, so good? So good. Let's go to our last property. We really like to take this opportunity to summarize all the important things for periodic function, right? And then that's going to help you a lot in the following, kind of have an overall understanding for this entire periodic function. So the last one, we're going to give you some generic periodic function, generic periodic related properties for our trigonometry function. We're still going to focus on trigonometry, right? The previous discussion is for generic functions, but our session is for trigonometry. So if I have a trigonometry function A sine omega x plus phi, of course, omega cannot be equal to 0. So the t for such a guy is 2 pi over omega's absolute value. Omega can be positive, negative, right? We just want to know 2 pi over omega's absolute value. A cosine omega x plus phi, t will be 2 pi over omega, exactly the same thing. Because like I said, sine, cosine is nothing, but if you just do quick switch, right? Move left, move right, and then you're good to go. And the tangent x, also omega not equals 0, is exactly the same thing, but you want to change this into pi, not 2 pi, right? These are both 2 pi, and this is pi. In our previous example, we give you sine x, cosine x, aka omega equals to 1. So you have sine equals to 2 pi, omega equals 1, cosine x 2 pi, tangent x equals to pi, right? But generally speaking, if there's a coefficient for basically sine, cosine, tangent, and you would be able to have something a little bit flowery, but generally speaking, I think this is very understandable. So far, so good? Any questions? Okay, perfect. If all good, so let's go for some other problems, right? Let's go for some other problems. So let's go for one problem. Basically using the definition of this, all those kind of like sine, cosine, so on and so forth. Let's go for such a question. Q5. We let fx equals to a minus 2 cosine x, 3 sine x. This guy is an increasing function on 0 pi over 2. Please determine the range of A. I have a function. This function is A minus 2 cosine x over 3 sine x. Okay, you have sine, cosine on the denominator and the numerator. I told you this is an increasing function from 0 to pi. So do you still remember? We keep talking about this. Increasing, decreasing, the monotonicity is more specified in a certain interval. It is quite possible that some function is increasing in some domain, decreasing in some domain. Let's say our sine x, right? Increasing, decreasing alternatively. So whenever you talk about increasing or decreasing, the most important thing is that you want to make sure you want to give a specific domain. Okay, our function is actually increasing in this specific domain. With all those information, please find out the range of A. All right. I see a function. Let's think about what is a thinking process, right? This is a function. I want to say this is increasing function, decreasing function, so on and so forth, right? But this function actually has two different things, two different variables. Let's say one is cosine, one is sine. Yeah, even though they both take x as the variable, but sine and cosine, they're two different things, right? They're not the same thing. If we have something like this, for instance, this is going to be easier for me to determine cosine, what is increasing or what is decreasing, right? So it looks like I have two variables at the very beginning. Like I said, even though they look the same, sine, cosine, they both use x, but they're two different variables, two different functions, right? So my goal is I need to basically reduce the variables, right? From 2 all the way to 1. If I can somehow do some magic, put cosine x and sine x both into one thing, then maybe the work is done. Is that right? So who can tell me, if you know, is there something easy way for you to make the cosine and sine into one variable, one tiny thing, and then taking from there, solve the problem? Have you guys ever heard about this? Because this is a very, very important mathematical common sense, right? This is very important common sense when you are dealing with the trigonometries. Now you have two variables, sine, cosine, but you want to convert it into one variable. And then taking from there, maybe I do some substitutions, so on and so forth, I can solve the problem. But now whenever you have two, you really have no idea what to do. So have you guys heard about it, how to do? If you guys went to the other math competition training courses, organizations, have they told you something about this? No? Okay, if no, let me tell you what you're gonna do. This is a very important conditional react. In our lecture, we're gonna teach you hundreds of tons of conditional react. Like I said, if every problem you need to think from the very beginning, that's gonna take you forever. You can't think too much. You have to use your conditional react, try to solve the problem as quickly as possible. So the first conditional react I like to tell you is that as long as you see cosine, sine, two variables, even tangent, three variables, you want to reduce to one. There is a very important formula you need to remember. That's the famous, we call it tangent half angle formula. Tangent half angle formula. What is that? Sine x can be written as 2 tangent x like this. Cosine x equals 2. 1 minus. Oh, no. Oh, excuse me. This is cosine here. Cosine is 1 plus. 1 minus tangent. Tangent x equals to 2. This is the famous tangent half angle formula. In Chinese, we give a name, we call it 万能公式, but not necessary. This is not necessary, 万能, I have to say. However, why we call it 万能? 万能 means just kind of like do everything, right? It actually means you can actually use tangent half x to represent sine x, cosine x, and tangent x. There's only one variable that's going to help you to represent the entire sine, cosine, tangent. So that's the very powerful way help you to reduce from multiple variables into only one variable. Trust me, we're going to see that formula many times in the entire course of our lecture. And this is only the first time you see it. You're going to see it more often in the future. So far, so good? Just try to remember this. There's nothing really tricky. Just try to remember this. Because as long as you do this, all the sine, all the cosine is going to be reduced just into tangent half angle. There's only one variable that you'll be able to do your calculation. So what we're going to do is fx is what? Still remember? A minus 2 cosine x, 3 sine x, right? X is between 0, pi over 2. So we're going to switch it using the tangent half angle formula. A minus 2 times 2 tangent x over 2, 1 plus tangent square x over 2. I'm going to rewrite it. 1 plus tangent square x2, 1 minus tangent square x2, 3 times 2 tangent square x2, 1 plus tangent square, 1 plus tangent square x2, right? And then to make our life a little bit easier, because there's so many tangent x here and there, right? Because x is between 0 all the way to pi over 2. So half x is between 0 and pi over 4, right? So therefore, tangent half x is between 0 and 1. Is that right? I don't think it's a rocket science, right? So that being said, I'm going to let t equals to tangent x over 2. So t will be between 0 and 1, right? Try to make our life a little bit easier. They're too much they're like too much denotations. So that being said, you're going to have what? You're going to have the entire thing is going to go to a minus 2 plus a plus 2 t squared 6t, right? I'm just going to do a quick replacement. There's nothing tricky. I'm just going to do a quick substitution because tangent x over 2 is not something that much easy. I just want to make it a little bit easy when you do the calculation, right? So that being said, your ft, right, is no longer, right, like x. You're actually changing to t. So your ft is going to become a minus 2 divided by 6t, a plus 2, 6 times t. You are telling me this guy, whenever t is 0 to 1, this is an increasing function. You wanted me to determine the value or the range of a. Is it right? Do you guys follow me? Let me have a quick survey. Do you guys follow me? We just want to do a quick substitution. The original x-related thing has been replaced into a t-related thing. Yes or no? Everyone, please give me some feedbacks. I just want to make sure we're on the same page. Okay, perfect. Okay, now I have to determine this guy as an increasing function between t equals to 1 at 0 and 1. So I don't have too much flowery things. Let's try to use the definition. What does increasing function mean? Increasing function means, let me try to use the color maybe red, okay? Increasing function means if I have t1 lesser than t2, both between 1 and 0, right? Increasing function means ft1 minus ft2 will be lesser than 0, right? A smaller, like smaller x corresponding to smaller y. This is increasing. Decreasing is swap, right? Smaller x greater than y. So let's try to do a quick calculation. ft1 minus ft2. Let's have a quick look at it. I want to make this guy lesser than 0. So I'm just going to plug in the value, right? T1, T2, plug in the value. I'm going to skip all this calculation process. This guy is going to go to here. Because our lecture focuses on the thought, right? The calculation, I'll leave it to you. You want to make this guy lesser than 0. Is that right? According to our definition, if this is an increasing function, I have two x. One is smaller, one is greater. If I do a subtraction, the smaller x fx will be lesser than the bigger fx. AKA, this guy must be lesser than 0. Okay. T2 is actually greater than T1. So it means this guy must be lesser than 0. Is that right? AKA, you want to means this guy greater than 0. So A is lesser than 2 T1, T2 plus 1, 1 minus T1, T2. Okay? However, where does question ask you? The question is asking for you, what is the range for A to make sure this guy is an increasing function? AKA, what is the range for A to make sure this guy is always valid? AKA, what is the range for A to make sure this guy is always valid? If I want to make sure the range of A to make sure this guy is always valid, who can tell me what is the common approach? This is also a critical important conditional react, and also a common sense, a mathematical thought. I want to determine the range of A such that this guy is always valid, right? So that one actually means what? Who can tell me? What can I do? What is the common approach? What is the common mathematical thought I need to do in order to determine the value of A? Okay, first thing first, we're on the same page. We want to determine the range of A such that this guy is always valid, right? On the same page. So that being said means what? I need to find out the range for A such that the A is always smaller than this guy. So therefore, I have to find the minimum value of the white, like the black box here. And I just let A is lesser than this minimum value. And then that's it. Do you guys follow me? Can I ask you a quick feedback? You are asking me to find out what is the range of A. I don't know what is my range of A, but I know A, you want my A to smaller than the black box, right? So that being said, if I can find out the minimum value of the black box, let's say 3, and I want my A is always lesser than 3, so therefore, regardless whatever value I want to choose, my A is always lesser than the black box. Do you guys follow me? This is a very important mathematical thought. You're going to use that from time to time in the high-level math competition. Can I have some feedbacks? Do you guys follow me? Yes or no? If you don't understand, please let me know. I will give you another explanation. Because you are trying to find a value for A such that this guy is always good, right? This expression is always valid. So that one actually means what? You want to make sure this guy is valid. So what can I do? If I can find out the minimum value of this guy, because this guy is a function, the function might have the range, right? If I find out the minimum function of this guy, And I always let my A lesser than this minimum function. So therefore, my A is always lesser than your expression. Because let's say this guy, the minimum function, let's say equals to 6. I just give an example. So this guy is always greater than 6, greater or equal to 6, right? It's a minimum function. If you want to make sure A is lesser than 6, then A is always lesser than this guy. This is actually using the boundary, using the scaling method, which is very important mathematical thought for high-level math computation. If we're on the same page, so basically I just have to find, I need to find the minimum value of 2 T1, T2 plus 1, 1 minus T1, T2, right? That one I think is very understandable. This guy is always greater than 1, right? Because T1, T2 is always minimum, T1, T2 is always value between 0 and 1, right? So 1 plus something over 1 minus the same thing is always greater than 1. So this guy will be always greater than 2. Is that right? So therefore, the minimum value of my blue part is actually equals to 2. I just to have, I need to let A1, I just need to let A is greater or equal to 2. That's good. Why I can equal to 2? Because this guy can never equal to 1, right? This guy equals to 1, aka means T1 times T2 equals to 0. But T1 and T2, where are T1 and T2? Where are T1, T2? They're between 0 and 1. So T1 and T2 can never be equal to 0. So therefore, this guy is always greater than 1. It cannot reach 1. So this guy will be greater than 2. You cannot reach 2. So that being said, A can reach 2 because you reach 2, but this guy won't be able to reach 2. So therefore, you can give this equal sign to A. I don't know if you can understand this tiny, tiny part. This is kind of like a boundary, right? If this guy can reach 2, then A must be lesser than 2. If this one cannot reach 2, then A can reach 2. This is not super important if you cannot really take the way around. That's not a big deal. It's kind of like some boundary condition, right? So this is actually the solution for this problem. This is not an easy problem because it invokes a lot of important mathematical thought, right? The focus of our lecture is trying to teach you guys as many mathematical thought as possible, which is extremely important for today's lecture. All right, a quick recap. In today's lecture, we introduced a basic introduction for trigonometry. It's kind of like some definition ideas. We're not touching too much about a weird like identities. Also, we introduced a trigonometry function. You can have an idea how this function thing works. In our next lecture, we're going to continue talking about the trigonometry function. We're going to give you some more flowery, interesting problem from a Canadian, American, and the other country exams, and hopefully you can get an idea of it. All right, that's pretty much for today's lecture. I hope you guys enjoyed today's lecture. Do you have any questions for me? Perfect. If all good, I wish you guys a good day, and I'll see you guys for the next week. Bye, guys. And also good luck for your upcoming AMC B part. Ciao, ciao. Have a good one.